So today we're talking about introduction of this, one of the main things of the course about supervised learning and the different types of learning. So we talked about this in the intro lecture. So I'm going to kind of overview that, and then we're going to talk about the first main area of essentially machine learning, which is supervised learning, which is where most of the methods fall into, and some specific algorithms in that. So one way of kind of looking at all this domain and different types of analysis is kind of an older way of looking at it, but you might see these terms places, so it's useful to know them, is that you're talking about different types of analysis of your data or your system, and in sense of what is the goal, what's the output you're trying to get out of your analysis, right? Are you trying to describe the system, or are you trying to make predictions or assign labels to it, right? So depending on what you're trying to do with your data, what the answers you have to, the questions you have to answer are, you might use different methods, right? Right, so if you're only trying to summarize data and explain it to people so they understand the trends and they understand the patterns and are making their own interpretations and decisions, there's different methods you would use, right? So you can do data summarization stuff. You can do visualization. So some of the things we'll talk about in feature extraction, dimensionality reduction are very useful for creating visualizations. And they're not necessarily helpful to help you automate anything for classification or making predictions or making some AI, but they're useful for people to understand the data better. Because if we've got, 100-dimensional data and the patterns are very hard to break out, we want to create charts that are visible and usable for humans to understand, right? So it's kind of its own area, and this course is on visualization, and it's a whole area, so we'll touch on this because being able to do a good description often helps you build a good model for prediction, but it's not the end goal. The end goal for most of us in this course, and for most times for engineers, because you want to build something, is inferential analysis. So you're trying to actually be able to make some prediction from your model that you've learned and do something with it concrete. But as people are finding more and more in deep learning these days, actually, is that the better your model is at describing something and understanding it and capturing everything in a compact way, the better it'll be at inferential analysis. And this wasn't really that understood until kind of recently, so they are still tied together, even though the second one is more what we're focusing on. So somebody's asked about the slideshows. That's a good question, because they are ready and available. I should just have them up there. So why don't I just do that quickly? I know sometimes it helps people. Where is it? Yep. Okay, I've dragged the two slide decks up onto Learn now. If people want to see them and go on their own way. Okay, I'm just looking at other people's concerns there about sound and video. So those are all very clear things. Yes, yeah, we're gonna. So Dhruv has a question about I'm going to be using different methods on data sets and coding. Yeah, so we're going to have a lot of programming. The assignment we'll release you this week will give you some specific data sets and ask you to use specific algorithms and some of the methods that we talked about last week and the ones we're going to talk about this week. I had a bit of a graph there before last week with you guys about the overview, that's this next slide, right? So you remember this one. So this is my kind of flow of breakdown of the data pipeline of, going from data to analysis and breaking it out and kind of turning it into a useful form, and then picking your algorithms based on your task and targeting it towards whatever, decision-making or analysis goal you have. So we're going to talk about some of these algorithms and actually some different ones. The difference between these areas is about the data that you have when you're doing your training, right? So we're going to talk about a simple classifier here, just to intro an algorithmic approach to start, called k-nearest neighbors, and the goal there is to classify data points to be the right label. So if we're trying to group people together from some data sets, so you have a census data set and you're trying to work out predicting how many cars some family owns, or how many something. Cars is a nice unit because it's hard for some people to buy one, and hard for people to buy multiple. But you could guess or label families that might have the ability to buy 0, 1, 2, or 3 cars based on other factors, right? You have information about their job, their income, the number of people in the house, where they live. So that's the thing you're trying to classify. And so for every new data point, which is like a household in your data set from the government census, you're trying to predict this label of how many cars do they own, right? And so supervised learning says you're given the answer, right? So I give you a whole bunch of data, maybe 80% of all of the data, and I tell you what the answers are. And so you have all the information and the label saying, oh, they have 2 cars, oh, they have 1 car. So it's called supervised learning. Classification is kind of the most common application of this. But you can have supervised learning for prediction and say, well, what's the next for COVID, right, is another great example. You want to predict a number that goes up and down over time, which is like the infection rate in some city tomorrow, and you want to use it based on past experience. And if you're training your model based on previous data where you knew the right answer, that's a supervised method, right? So linear regression, logistic regression, prediction, and classification are all in here. So most of the things people want to do in machine learning are supervised. So the other flip of that is unsupervised, right? Where we don't have the label. So this is generally harder, right? Because I'm asking to learn a model that's useful for maybe prediction, maybe classification. Essentially, when you're doing classification where you don't know the labels in the first place, or not given to you, we'll call it clustering. We say, well, let's group points together just because they're similar. I don't know what the label is. I'm not saying they're buying 1 car or 2 cars. I just know these data points are similar, and so it must be meaningful that they're close together in some way. So that's called clustering. So unsupervised learning is harder than supervised learning because there's a piece of information missing, but you still got to learn something. These can be thought of as more as descriptive models because you're essentially saying, I want to build my algorithm so that it understands the data, but then I have to use it for something meaningful. Whereas supervised learning, we don't care how the model is represented or whether it's correct or not. In terms of, correctly in terms of we want the prediction to be correct, the label, but we don't care how it gets there, right? So sometimes the trick will happen, and we're going to talk about this either at the end of today's lecture or tomorrow, is that if you overfit to something and you're training just on a very specific piece of data, supervised learning approach can get you the answer that's correct and you get it right 100% of the time, but it's essentially cheating because it's using some element of the data set that isn't really about fully understanding it. So we'll talk about that after. And the third kind of major area that people often put is like categorizing machine learning, and in the Kevin Murphy book, this is how he divides it up, is reinforcement learning. And in this case, it's not only you don't have the labels, but you don't even have, well, the first thing is that you're making decisions over time. So you have to basically, it's more like for a robot or for driving or for a person deciding what to do based on past experience. But you also don't have information about how the world works. So you don't know how things change from one moment to the next. and you don't have labels about it. So this is even harder, but it is closer to the kind of learning that humans do, because a child learns through reinforcement. They essentially see things, they make some choices, their parents tell them very good, they tell them very bad, they give them a cookie, and then they do better the next time. And so the idea is that you iteratively improve your model through experience, right? So we're not going to get into this here, but they all feed from the same sets of methods. So the things that you use in supervised learning are necessary for all of these, but it's kind of the core task, really. So we have some questions. What does that sound in the back? Nice, okay, so I know how good my microphone is. My wife's making, blending a smoothie or something, so there's some noise in the back. Hopefully it's over now. I'm in a completely different room, but blenders are very loud. Can we say a cluster is given a name value? When a cluster is given a name or value, supervised learning. So there is this question about whether, now let's see if my pen will work, is the other part I want to get working here. Oh, it does, okay. So what do we say? Clustering, someone's asking if label's known, is it classification? Not necessarily. If they're known at training time, right? So if you know at training time, when you're training your model and the labels are available, then they're known, right? But if we've got a bunch of data points and they have labels, but we're not telling the algorithm what they are, right? So these are the people with 1 car, these are the people with 2 cars. But if we don't give these labels to the algorithm when it's doing it, then it's unsupervised, right? So it could be that you, as the modeler, know the labels, but you're not giving them to the algorithm because you're trying to train it in a way that to prove that it can learn the essence of this data without giving labels. But if the algorithm's given access to that, then it's supervised. When you don't know the labels, right? So even a modeler doesn't know what these are. Then it's clustering really, because then you're just making really subjective senses saying these data points are together and these ones are not. And it's actually, you have to justify why some labels are correct or not. So that's why it's also much harder, because it may not even be that well defined that these data points should be in this point or that point, right? I mean, now that I'm on label here, I can't change my pen color. You know, it's questionable whether this point here is actually in the first cluster or the second cluster, right? And so that's not about the data missing or not, it's fundamental. All right, cluster contains groups with Euclidean distance and similarities. Well, you can have other U-distances. So the way we're going to define these distances and whether something's a cluster is about whether things are close or similar. And I think you had lectures already last week on similarity, so we'll use those methods and some others later to say the points are similar. It doesn't have to be Euclidean. It could be any method that says they're similar or not. It could be differences in bit values and anything, right? All questions about reinforcement learning. Reinforcement learning is my area of research, and I love it, so I can definitely share you guys resources about it later in the course, and we can talk about that. But as people say, Richard Sutton's book is a good starting point. I run an undergrad course on that, so we have lots of resources available as well. Validation. We'll talk about validation a bit when we get through the later part today or tomorrow about tuning your model, right? So we talked about if you watched the videos last week about training, validation, and testing. The training and testing is kind of the most clear, right? Because you've got some stuff you train your model on and some data that it never saw that you test on, right? But Sophia is asking about, oh, sorry, Sophia's answering someone else about validation. Validation is more about before you fully train it for reals, you kind of use the validation set to tune some of the other parameters of your algorithm. So for this KNN algorithm that we're going to talk about, the only parameter you have to pick is how many clusters are you having. And how many neighbors are you using, sorry, in order to classify it. And so that's a parameter you have to pick, right? And so once you pick that K, it kind of affects the whole way the answer of the algorithm is going to be. So how do you pick K? You don't want to just commit to K equals 3 and then get the answer and say that's a result. So the validation step is to let you have a loop where you kind of try out different values of this parameter, and you don't really know what K is yet because I haven't explained the algorithm, but that'll come next. Oh, I have my pen today. So, and then once you figure out, you do little experiments on each of these, and once you figure out which one's really good, you stick with that, and that's what you use for your test data, and for your training data, right? You actually train it on using that value. But the validation step is kind of this precursor to let you pick your parameters. How did the poll go? 80% of people were fine with the sound and 16% were not. Okay, we can have another poll, custom poll. And there's no way to enter a description. Okay, so if you're having trouble with sound, I can't do, I guess my question was, if you're having trouble with sound, are you in North America, India, China, elsewhere? I think elsewhere is less people. Only for people who are having trouble hearing. We could try to figure out if it's data connections or if there's anything in common between everyone. Okay, so some examples of the differences between cluster and classification, just breaking down different things. It's not complicated, but like I said, classification is supervised, so we know the labels, right? We're given the labels. We have to have a training phase beforehand for classification because we need to learn a model, given the labels, try to learn those patterns, and then work with it and give us an answer. Clustering, you kind of skip the step. There's no, doesn't have to be a training phase because it doesn't know the labels anyway, so you want to set it up so that it'll work right off the bat. But you're using similarity scores and existing patterns in the data to help you determine whether data points are similar or not. Classification things could be domain sensitive because you've kind of trained it on these specific labels and data, so it's really only good for that. That's the problem of overfitting we're going to talk about. But it's easy to evaluate once it works because you know the right answer. You just see how well it did on the test data that you held out. Whereas clustering is hard to evaluate, but it might be more general, right? More generalizable because it had to get at the essentials of the data. And so often, if you can do this, it's kind of very useful. It's just that you don't know if you're right or not because the right answer isn't given. And so these are some of the algorithms. This is the kind of the biggest, famous, easy algorithm that we'll talk about in not too distant future. And I mean, neural networks are in here as well, but they're their own areas, and most of that will be classification and clustering as well. Most of the algorithms we'll talk about will be there. Some people saying the sound got problem. Yeah, the question of the poll. Logistic regression. Logistic regression, Ashke is asking, is like classification, right? Because it helps you decide between multiple classes and gives you a probability of one being right or the other. And we will talk about that a bit too, because it's one of the basic classification methods that uses probabilities, and is kind of analytically simple. And it's very related actually to neural networks as a very simple version. Okay, so we've already talked about some of this before. Classification for learning from training samples. So we have our features that describe our data, and we're trying to fit a particular label to that. We have our test labels. Right, so discrimination of classes is kind of one of the big tasks, right? So the word itself is maybe a bit awkward, but we're using it in the sense of you want to discriminate between a bunch of points, right? If we can say, well, these are clearly two different sets of points, that we could draw a line between them, and I can tell the difference, right? But if the points were closer together and didn't have any way to distinguish them, then it's harder, right? And so what you're really always trying to do is come up with some way to distinguish the points, to discriminate between the ones in one class versus another. And sometimes that's easy, sometimes that's hard, but that's kind of the main task, right? And it's related to prediction because you're just trying to come up with a discrete label. Every class is kind of rounded up to some label, but it doesn't necessarily have to be something smooth or a simple function, right? Right, so the question is, how do we do this? How do we take some of our input data and learn a model that can tell us in a general way that those data points should be labeled a certain way, and how it can be done for general data sets? Uksha's asking, what's the difference between a feature vector and a regular vector? A feature vector is just a vector of features. So it's an array of numbers, right? There's just some notation we'll use in various things. So for the k-nearest neighbor, we're going to use, I think we're going to use this notation of how many neighbors a particular point has. But if you think of our data, right, you've got a bunch of data points, right, and each one of these data points has a number of features, right? So our label y is going to be the thing that we want to predict, right? So when I was talking about the number of cars people have, you know, it's just going to be this label. In this notation, we don't have features listed. The easy way to do it is just to call it f, and we've got features describing this, right? So like I said, in the census, it could be, you know, income, number of people, it could be the area code and the address, other stuff. And so for every person, this is a vector of features, right? That's all. And sometimes when we're talking about x being not just one element, but like each of these data points x is a vector of an entire set of numbers. Sometimes in a notation we'll have it as like a very bold thing to indicate that it's a vector of numbers rather than a single number. Other things that will show up, so what you see for class label, indicator function will show up in some algorithms. Yeah, it'll show up in this one. The indicator function, right, is something that is like you need to have if statements. Your program has if statements, and in math you want to have an if statement sometimes. And so if you had a bunch of data points where the features had a certain value, you could just have an indicator function that tells you something about it, right? So say this is x, and then I of x, I'll move this over, the indicator of x is greater than or equal to, sorry. The only problem with this program. X is greater than or equal to 2 would be, it'll only be true in the cases where that's true, right? So it'd be true in these cases and 0 in that. So you get a binary vector, a 1 or 0, if some condition that you give in there is true. And this lets you sum over everything, right? So then you can do something like summing over all the values of x for some condition, right? And you'll get a sum of all the values, only the ones that satisfy it. And then we'll talk about kernels at the end a bit too. Yeah, we'll talk about that when we get to it. Great, people answering each other's questions, that's good. Yeah, the lectures have been posted up on Learn now, so you should be able to download them. So what's classification? Mathematically, we want to say that we have a data set of these data points, and it's got a number of features in every data point, as I was saying. And we also have a set of classes, right? So in my case, for the number of cars a household owns, you're trying to predict that number for each of these data points, which is a household. And the problem is really to learn a function that goes from x to c, right? In any way you want to do this, right? And all the algorithms we talk about in classification are essentially ways of learning a mapping that gets from this data, from this table, to some set of discrete values, right? So any way you can think of doing that is classification. Yeah, a class is also a class is a partition. The classes are a partition of the space, right? So once you've assigned a class to every point in the space in the data set, there won't be any data points left over. There won't be any classes left over. It could be that no class had any data points assigned to it. That's possible. Nobody bought 5 cars in our data set. The elements of that is empty. Every data point is mapped to exactly 1. So we'll see the indicator function just used in one of the notations for defining the second algorithm we're going to talk about, the parse window. So these are just general concepts for what you need to consider, right? So we've talked about data, we've talked about classes. What if data points can have multiple classes, right? How would you set that up? What if data points overlap and they kind of belong to more than one class, but you really want to come up with a single class? Is your model going to get confused? That's an issue to kind of, as part of your design when you're choosing the algorithm, it could be important. Missing values, we talked about data cleaning last week, and like replacing missing values with kind of interpolated ones, or if you're missing data points, what effect is that going to have in your algorithm? Some algorithms are very robust to that, and some of them are very sensitive to it. These are all things to think about once you know the different algorithms, to worry about whether it's going to work well or not on your problem. And then we have to be able to estimate our error. And so the lecture for tomorrow is all about how to evaluate whether your classification is working or not. So different accuracy levels, but also there's ROC curves, which help you. They help you with the parameter tuning as well, so they can be useful for that validation step. But that's another method, another thing we're going to talk about. So let's talk about this first one. So it was about the k-nearest neighbor classifier. And